Okay, now we come on to more advanced discussion of Apache Spark, looking at its treatment of machine learning, both but in Spark and other approaches. This is a critical part of big data because you have your data stored on files or in HBase, NoSQL databases or RDDs, and you'll want to apply some processing to it. And machine learning is obviously a hugely important way of processing data. So let's get going. I'm Jeffrey Fox, your fearless lecturer. Okay, here we have our separator slide saying the same thing, and we will now move on. All right, so this work describes a little bit of context of MLlib and what Spark does, because we have a project within the Digital Science Center at Indiana University, which is essentially generating a rival library. It was called SPIDAL, Scalable Parallel Interoperable Data Analytics Library. And here we compared it with what happened to be standard when we started the project, Mahout. Mahout is, of course, now deprecated somewhat and replaced by MLlib, but they're very similar in terms of concept, have similar types of capabilities, and we will compare that with what SPIDAL has. SPIDAL has some general machine learning algorithms. Then it has a very special set implemented by Judy Chu, which uses HARP technology plus Intel's specialized data analytics technology. DAAL works on the node, and Judy's HARP system coordinates the multiple nodes together to run a giant parallel job to get the world's fastest, best machine learning. SPIDAL has these general things, such as these ones in Mahout, but it also has the particular algorithms used by biomolecular simulation, network science, polar science, and pathology. Okay, let's get going. Here is the actual list of the SPIDAL library. It's about somewhat over 20 members, and it lists the name. Here's multidimensional scaling, which is a dimensional reduction routine with some nifty technology called deterministic annealing (DA). Here's another approach to dimensional reduction, which is quite similar, called directed force. Here we have various clustering algorithms. As we note later on, there are various forms of clustering. Some for vector spaces, some for non-vector spaces where any distances are described. That's what symmetric means, no vector space. We have the basic KMeans. This one up here has deterministic annealing to improve it for either a non-vector or vector situation. Support vector machine. Here we have a very important graph algorithm trying to account and identify subgraphs of a particular shape. Here we have the famous topic modeling algorithm, latent Dirichlet allocation. We have matrix factorization used in recommender engines, SGD, alternating least squares, singular value decomposition, QR decomposition. These are all matrix algebra neural nets. And these are very simple basic statistics algorithms, regression, used for classification, random forest again, and PCA, which is the simplest dimensional reduction routine, where you find, which is again matrix algebra, because principal command analysis finds the leading eigenvectors of a giant symmetric matrix. Here, this just sort of illustrates, as an aside, what happens when you do clustering. This one here in the bottom left is some results from a proteomics clustering application. The yellow things here are the cluster centers. The orange stars are lonely points which were not clustered. Not very many of them. Most things form into a cluster. And you can see some interesting features that sometimes, like this case here, the cluster is reasonably separated here. But in other cases, like here, all the clusters are together. And it's pretty important to know what you have, because if you have when you think about clustering, you think of actually two separate clusters, big white space between them. Those you can really have wonderful algorithms to find those in incredible accuracy. But the real world is like this. The clusters are not separated. Now you can ask how I know this is 8 clusters and not just one. It's because I know the size of a cluster, because the cluster reflects the error in the measurement. So this is some proteomics measurement, and we have an error which is shown by the dispersion of the points from the center. So we know that there must be lots of clusters here, but obviously, as they're so close together and sort of overlap, it's not going to be terribly easy to get a unique solid answer. You can just get good answers, not solid answers. That's very important when you do clustering. Please find out whether your system has clean clusters or not so clean clusters. Here's an example here which actually has cleaner clusters, so it's not so obvious from this picture because it's projected. This is a high-dimensional space. This maroon cluster here is actually pretty distinct. If you looked at it in 3 dimensions, you would see that it's actually separated rather cleanly. And genomic data has this feature that the different species and families are actually separated by typically more than the measurement error, which is dispersing them. And here we have actually this particular data set has 200 clusters, and this is found by the deterministic annealing clustering algorithm, which is needed for these rather difficult problems to get robust answers. But I think most clustering is actually the point these clusters are joined together. Even here, you have some clusters joined together, like some of these. Not so clear from here, which you have to look at it in 3 dimensions to see which are separated. But I think some of these ones over here are actually very close to each other. But there are a lot of cleanly separated clusters in this data set. All right, so now let's look at the K-means algorithm in detail. If you look at clustering algorithms, they're not only, there are lots of them, not just vector space versus semi-metric, which is when you just have a distance, but also they make different assumptions. Some have errors, some you feed in the errors, some you don't know the error, so you don't feed in the error. In that previous example, the first one, which was the proteomics, fed in an error. The later one, which was genomics, you didn't know the error, so you didn't feed it in. But then anyway, in typical simple K-means, you must feed in from the user the number of clusters, or which is effectively the same as the number of centers. And your first initialization step is just to randomly or systematically assign all the points to a particular cluster. And let's say we'll do it so that every cluster has the same number of points. So we get a good solid number of members of each cluster. So the basic iteration is to refine the cluster, or if it's just the initial choice, we've already done that. Then we find the center of each cluster. It's easy to find the center of each cluster. If you assign 603 points to that cluster, you just take just form the geometric center of the thing. Add up all the vectors and divide by the number of points, 603. That gives you the mean. That is the center of the cluster. Given we have the center of the cluster, we have to decide whether we calculated the answer or not, which you do by comparing the differences and how far the centers are moved from iteration to iteration. If it's it's still moved a lot, or it's right at the beginning, we just go back and iterate this. And you will find that it converges quite fast, depending on the accuracy. If it's a very accurate case, like the genomic case, you might want to have thousands of iterations. If it's a very simple case, like clustering grocery items for doing recommender engines, then you can probably run half a dozen iterations. So it all depends. But you need in clustering to know your goal. Different clustering problems, different applications have different goals. Okay, here we come to the sort of more formal specification of this. You load the points into parallel into the different tasks. You initialize the centers. And then you iterate the following graph, following code. Here we take the points and find the centers they're attached to, and then we do overall, and then they also calculate the centers from those points, and then we do a total overall reduction, which adds up the contributions. Each cluster will have contributions from each task, so in general the points will be spread over tasks. There will be no locality. Points for cluster number 1 will not all be in task number 0. They might be spread out over all tasks. So you need to do a reduction to find the final centers, which you may then follow by a RDD, but you would then iterate this graph until either the number of iterations is finished or an error count is finished. And what this also points out, that this is data flow in different granularities. Here is the data flow within Spark, where you have your basic map functions complete, which are running here, and then the reductions. And then we also have we might have an overall data flow, which has KMeans is just one node in that overall data flow. It could then be followed by a dimension reduction and a visualization of separate steps in a pipeline. I mentioned earlier the pipeline is one of the most important directed cyclic graphs. So here we have some K-means clustering results for comparing Spark, Flink, and also the high-performance computing implementations that we like to do. Uses either HARP or MPI. This one is MPI because it's so simple. And you will see that at least for some cases when there are a lot of centers, MPI outperforms Spark and Flink by a factor of 100. And this is shown here against the function of nodes. As you look at least that's Flink, it actually runs slower on 16 nodes than 8. Spark does at least continue to run faster, but actually it's always running slower than either Flink or MPI. MPI does get faster as you increase the number of nodes. This will notice that these are done for different choices of number of centers. Here we got the most extreme cases for large numbers of centers, where efficiency is more important because you have more data communication and reduction to be done. When here is a medium case, 64,000 is this case here. And so there's not these huge, this is more like a factor of 20 difference between Spark and MPI. Here's an even more extreme case, multidimensional scaling. It's a much more complicated algorithm with actually 3 sort of separate different parallel steps. And you can see that for all these points, MPI trivially outperforms Spark and Flink. In this case here, Spark actually is better than Flink. Flink gets a bit lost in this problem, forgets where things are stored, and does a rather inefficient. Remember, you would need to do the other compute rule. You store the data on the node that does the computing, but Flink can't get that right. Here is the data flow graph, which is quite complicated. And here we have a log graph, which is why they still look reasonably close, defining for 32,000 points, which is this case here, the dependence on the number of nodes. You see Flink is actually getting slower. Spark is getting slower as you increase the number of nodes. MPI is doing what it ought to, getting faster. You can note also an interesting feature of this graph here, that there's a green and a red thing which are almost on top of each other. The red is the total MPI time, the green is the compute time, the actual time doing arithmetic. And all this other time is screwing around. And so Flink and Spark have almost the same arithmetic as MPI, so that green graph will be roughly the same. But you can see they're doing all restarting tasks, doing inefficient reductions, and just making a general mess of it. All right, we want to look a little bit about data, and here we have a little discussion about we can of course run Spark on top of different data systems, HDFS, NoSQL databases, object stores, or anything that Hadoop supports. And then we can also use different schedulers. Mesos is sort of the default, although it has its own built-in scheduler. That's the one here. The Mesos is produced by the same group that actually produced Spark. Yarn is the scheduler which came from Hadoop. And you can also run it not only on with different schedulers, on different systems. Amazon EC2, Azure, HPC cluster of any type, such as the one at Indiana University. So you are very flexible. All these systems here have pretty similar characteristics. And these data systems, they can all import data, the standard importers that will get you to Spark. Spark does have to have a file system attached to it. That's true of all these big data systems. And my HDFS, although it actually corresponds to Hadoop, it is the default file system for cloud data because it supports this data locality, which all the owner computes for, where it actually controls the data on the compute nodes. The in-memory database can produce a lot of memory use, which could be tiresome. And with all parallel algorithms, you shouldn't run small jobs on it, at least not on parallel versions of Spark, because they'll be inefficient. MLlib is not really complete, but it's still a good start. And Spark streaming is not so good. We pointed that out already. This plot here is sort of a cosmic plot. Tells you what's hard and what's easy in the world of big data. This thing up here is KMeans, is what we described here. It's actually reasonably easy. I put it out here at the, we have 3 classes here, totally loosely coupled. These are what I used to call map only, or classic map producers in databases. Map only is pleasingly parallel. And then we have global machine learning. It's sort of more complicated as communication, but it's reasonably structured. Many of these machine learning algorithms, like PCA, are linear algebra at their core. Deep learning is also linear algebra at its core, but slightly more complex. Sparse matrices are often involved. And then we have really complicated algorithms, of which perhaps the worst is graph analytics. It can be very messy because the details of the graph make for the graph is very irregular, and that irregularity varies across the graph. That is the hardest type of problem to do. Latent deletion allocation is also quite hard for related reasons, because the different documents you're processing have very different word representations, and therefore it's very difficult to get balanced loads. I've also put in red here classic simulations. There's structured simulations. That's actually what we started with. Maybe they were over here in this cosmic structure, but now we have complex structured simulations where the meshes are not very irregular. And up here we have adaptive complex meshes defining irregular fluid flows when turbulence and things like that. And at the bottom here, we have exascale supercomputers running these things here. And we have commodity crowds, because you don't need high performance in anything for commodity map-only applications. And in between, we have what I call an HPC cloud, which is cloud-like design, but with high-performance interconnects to get the performance you need. Here is a picture of Harpdal, showing that you have here the machine learning applications and the data analytics. HARP has a very particular computation model, which it invokes in its library. We have 2 types of data sets, the training data and the model parameters. We have a good communication library. We have all the wonderful work Intel has done They build on previous work from the high-performance computing community, which makes a parallel matrix algebra very fast, and then we have wonderful hardware platforms such as Knights Landing, Intel, standard Intel CPUs, and if we weren't doing Intel, we would use NVIDIA on this thing here. But HARP is designed for Intel, at least HARP DAL is. And so this is our general architecture developed in the Digital Science Center for doing the big data analytics. And in game, we would have, like everybody, a Python interface, because you can invoke the libraries from Python, and the overhead of Python is not important, because not much arithmetic is done in Python. And this middle layer is what we have here. And then with the lower level, we have DAL, and BLAS, and things like that. BLAS is basic linear algebra subroutines used for parallel matrix algebra. All right, here is actually the GitHub of HARP, and anybody who wants to work on it, please volunteer. Very exciting. These ones I've already shown you, and we put it out on GitHub in 2017. And each of the DAL algorithms corresponds to a particular, which is a parallel multi-node application, corresponds to a particular Intel DAL internal node application. Almost finally, we have here results on for HARP compared to Spark. This is the KMeans. Again, I showed you HARP Spark compared to MPI. HARP also outperforms Spark easily. Here we have HARP compared to Torch, another major machine learning for Python for principal component analysis. And here we have the hardest bottom, and it's HARP compared to a highly optimized MPI code called Fascia. And again, HARP manages to outperform it. The biggest factors are when we compare to the sort of might call the crude commodity systems like Spark. These optimized systems, and you really have to work very hard to do better than those. This makes a decision about, this is now discussing streaming, and this thing here just points out that streaming data, you really need to make decisions in milliseconds, or maybe even microseconds if you're doing financial trading. And that is not really compatible with sitting down at a table, or sitting down, or even scheduling a job on your supercomputer and waiting 2 days for it to come. But anyway, here we have the time scale here, and the type of job here, and now we're looking at this here. And it's worth noticing typical numbers. It takes milliseconds, or tens of milliseconds, to transmit data across geographically distinct areas. It takes a millisecond or so to wake up a Java program and do something. If you invoke an MPI routine, it will have microsecond latency. So, and whereas what is the typical execution time? It's nanoseconds. So we have 10 to the minus 9 nanosecond, 10 to the minus 6 micro, 10 to the minus 3 milli, and we have multiple days, which is what's happening over here. So this is illustrated for Apache, Heron, and Storm, which are come from Twitter. They're the streaming data systems. And you have here a Totalbot, which is a sort of prototypical robot. That prototype sends its data to a gateway, which is going to translate from the ROS operating system within Totalbot into a more mainstream environment down here. Then it goes to a bunch of, all the data is always queued. That's done in technology like Kafka, RabbitMQ, ActiveMQ. And then it gets sent off to here, where it's run in this workflow. This is again a DAG. This is a streaming DAG, which basically processes the input data with these buffers holding the data in queue, so we don't or supply too much data to the problem. And then finally it sends all the data back to the robot, and you can do this in hundreds of milliseconds. So you will not do this complex architecture unless you have hundreds of milliseconds, partly because it's going to take you tens of milliseconds to transmit it to a nearby cloud center, and maybe 100 milliseconds to a long way away cloud center. So here, the last two slides are just describe the operation of Spark with Docker. They're really independent of the lectures because they're not really describing Spark. And it tells you how to run the Spark using a Docker image, which you can fetch from the Docker Hub. And this has the Apache Spark and Hadoop Yarn. And we can run Spark in different modes. And we can adjust the different execution of Spark Pi and see how they run on different models. And then we can, of course, experiment with our own codes. So have a great time. Spark and Docker are state of the art, and thank you very much.